So, good day everyone. Today's lecture will be recorded. Today's lecture is about electrons in the periodic potentials. We will continue understanding how electrons are moving in the lattice in order to understand how to build the theory of electronic conductivity, taking into account the periodicity of the lattice. And the main concept which we will cover today is called the Bloch theorem. So, just as a historical remark, in 1929, the Swiss physicist Felix Bloch has introduced this theorem. Felix Bloch. So, note that it's approximately the same year as the Sommerfeld theory, which we have covered before, but now we will introduce the crystal structure. And just a couple of words about Felix Bloch. So first of all, we are here having these lectures in Switzerland, and it's very important that part of this course is covered by this theorem by a Swiss physicist, and more importantly, also he got the Nobel Prize in 1952. But of course, on the other topic, because you cannot get the Nobel Prize for a theorem. And actually in 1954, he became the first director of CERN. So, you can write down a couple of theorems and become a director of CERN. So, he's quite an interesting character, so check him out. So, today we're gonna discuss his theorem, and we'll do it from different perspectives. As always, we'll try to first build our intuition on something a bit simpler. Then we will write down the theorem itself, and then we will prove the theorem exactly. So before going there, let's just make a very brief recap what we have introduced last time. So last time we have introduced the crystal lattices. In particular, we gave the definitions of the Bravais lattices, the unit cell, the basis vectors, the Brillouin zone, and the reciprocal vectors. And we have done it for multiple purposes, and the main purpose was that crystals are themselves quite complicated structures, and they have quite complicated geometries, symmetries. It's not that we don't understand it, we do understand it, but we want to have some shortcuts to work with them just algebraically. So, and for this, we have introduced the Bravais lattices, which are constructed on all the possible translation vectors, which I will notate as A. So in one dimension, you need just one translation vector. So let me denote it as A1. Then if in 2 dimensions you need at least 2, so let me add the second vector here. And in 3 dimensions you need 3 vectors. So let me write it 3. And for this lecture I will mainly write it in the column. It doesn't matter if you write it in the line, but just in this way we can kind of quickly distinguish between 1, 2, and 3 dimensions. So this will be in 1D, yeah. This is in 2D, and this is in 3D. So, and here what we have introduced is A1, A2, A3 are some vectors in the real space, which are called the basis vectors. Basis vectors, and 1 and 2 and 3 are some integers. All right. So, and very similarly, we can introduce the vectors which will characterize the periodicity in the reciprocal space. So we have denoted it as J. And again, in 1D we need just one of it. In 2D we will add an extra one. And in 3D we need to use 3 reciprocal vectors, B1, B2, B3. So it's our guy. So again, B1, B2, B3. I call it reciprocal primitive vectors. I will call them just reciprocal vectors. Reciprocal primitive vectors. And we know that they are related with the vectors A by just an equation like this. So every time once we set our probabilities, once we've chosen the basis for vectors A, then we can find all the reciprocal vectors from this equation. So the scalar product of A times B is equal to pi times delta function ij, right? So again, maybe it looks a bit abstract, but it really simplifies all the formulas, and we don't need to think every time we are doing integration in real space or reciprocal space. We don't need to think about symmetries. We don't need to think about geometry. So once we've set the so this thing will set as the unit cell, and this thing will set as the Boolean zone, the first Boolean zone. So and then all the summation and integration can be reduced to the integration over the unit cell or integration over the Boolean zone. Now, so our purpose here is the following. So we want to actually solve the Schrödinger equation. So this is the so-called the single electron Schrödinger equation, which means that it knows and it describes only the behavior of one electron. So this part is, as always, the kinetic part. This V is the external potential where the single electron is moving. E is the energy of the electron, and psi x is the, so this is a complex valued wave function. All right, so I don't know, can you see it? So now our problem is the following. So we know that electron is moving in let's say inside the metal, so it has some certain crystal structure, but we don't know exactly the function v of x. And in principle, we can hide all the lattice periodicity, all the effects of interaction inside this potential, and introduce some average potential v of x. So this is like the main idea of what we can do within the this formalism. Now, how you can imagine this potential v of x? So you can think about it as, let's say, you have crystal lattice. Let's say we are in one dimension. So you have a set of atoms, which I will denote as these circles with cross. and these atoms are somehow create the potential well for the electrons. So there will be some drop in the potential here. Right? So the way of thinking about this equation, about this potential V of x, in the simplest form, we can just think about it as the sum over all the atoms you have here, and like each of the atom just gives a single potential coming from this atom. So let's say the potential which is created by one atom is some U of x, which, for example, comes from the Coulomb forces, then all the other kinds of interactions if we're gonna treat the system self-consistently. And so here we need to sum over all the atoms. So what I will gonna do is I will actually add here the atomic positions which will actually be given through this vector A. And let's say we are in 3D or in 2D, so I can put vectors here. Right, and then the sum over all the atoms will gonna mean that we need to sum over all these translations A. And in particular, so one can check that this potential will be indeed periodic. So if we add some A prime here, so within this sum you will shift the argument by A prime. Okay, let's gonna do it. You have this, so here you shift it by A prime, but you still have minus A. Right, so now you can introduce a new vector A with 2 primes, and since nothing will change if we will shift this, if we will shift this vector A by any amount of n1, n2, and 3 this vectors, so this sum will just simply will rewrite as the sum over all the A with 2 primes, U of x minus A 2 primes. Okay, I hope you can see this. So long story short, what we are recovering through looking at this formula and at this formula, that this potential is indeed periodic, so V of x plus A is nothing but V of x. And in particular, what it means for us is that once we're working with the Schrödinger equation like this, with the periodic potential, we can actually make the Fourier transform. And since we have here only the sum only over these translation vectors in the real space A, so the Fourier transform will actually simplify quite a lot. And so we can rewrite the same formula in the following way. So instead of the summation in the real space, we can go to the summation over this reciprocal vectors j, and now you will have some Fourier transform quantity Vj, and the exponents will just go with the vector j as well. All right. All right. Now after this relatively brief recap, we're gonna start introducing the Bloch theorem. But before writing down the very Bloch theorem, we will do two sketches. Like we will do sketch number 1, sketch number 2, just to build certain intuition in this theorem. So let's start with Bloch theorem sketch 1. So let's consider just a one-dimensional system. Let's write it down. Consider 1D case. And also as a remark, we will consider a set of wave functions which are non-degenerate. What it means we will understand a bit later. So if we have this like one-dimensional system, so we have something like a chain of atoms, each placed on the distance a from each other. So this distance is a. So let's say I will label them. So this atom has number 1, this atom has number 2, and so on, you know, until n equal to some large n minus 1, and this is equal to capital N. So in other words, we have n atoms in the 1D chain, and then we have electrons which are propagating on top of the effective potential which is created by these atoms. So what we're gonna do, what we want to solve is something like the one-dimensional Schrödinger equation. So now it will have a simpler form in 1D. I don't need this bracket. And again, we will impose that since our crystal lattice is periodic, the potential created by it should be periodic, at least in the terms which we have discussed on the previous slide. So what we will demand is, so we will have this equation, and for this we will demand that v of x plus a is equal to v of x. And we can do multiple shifts like this. So now there is a particularly nice trick what we can do with this system and kind of introduce the Bloch theorem in its toy form. So what we can do is imagine that this is some kind of metallic rod, like quite long. So like imagine n goes to infinity, something, a very thin rod. So what I can do, I can take this rod and connect its ends together and glue them. So At least you can do it in theory. So, but also, in principle, you can do it in the experiment. So we've taken this one-dimensional line and we've connected the the ends of it. So let's say we have had the atom which was number 1. It was here, and the atom number 2 is here. Let me draw the rest of them. So I'm drawing a relatively small number of them, but of course you need to think about it in the limit when n goes to infinity. And by infinity I mean the solid state infinity, which is something like 10 to the power 23 of atoms. So it's physically large. So we have something like this. So once we connect it, it's like this snake Ouroboros. So it's eating its own tail. So it has had his head here, you know, and its tail it's here. So the atom with number n, which was used to be here, is now here. And of course, this construction, it's of course physical, but it's also might sound a bit artificial, because now we need to have a perfect glue in here, which means we need to have something which is called the periodic boundary conditions. Which is a very often thing used in physics. So, and in particular, this periodic boundary condition would mean the following thing, that when we will glue the wave function here, the wave function, so the wave function shifted by n times a, so when we come here, should be equal to the wave function in the beginning. So the head of the snake should merge with its tail, the head of this quantum snake, because psi is it's a complex function. So yeah, so this is our kind of little small trick, and actually this trick will be used quite often in physics. For example, if you want to derive, well, actually a number of things, but in particular, if you want to derive something related to quantum Hall effect, you do a very similar thing, but with the Brillouin zone. Okay, so so we have connected this atomic chain in this ring, and let's see what happens. So let's say we sit first in the atom number 1. So we sit somewhere here, and then we make a shift in position by the unit of a here. So what actually will happen with the wave function if we shift by just a small step? Well, strictly speaking, it can shift only by the phase, but let's imagine we don't know this yet. So we will use that argument a bit later. So let's say we have shifted this wave function just by a, so the total wave function of this ring, and so what can change is that instead of wave function which we have had in the position x, we need now to multiply it by some factor c, and this is actually some complex, just a complex number. All right. So at this point we know nothing about c, but because our wave function is the c-valued function, complex valued function, the only thing which can change is like one complex number will go to another complex number, and this prefactor is is kind of shown in this number c. Okay, so that's fine. So now imagine we shift on one more a, so we now go here. So after the second shift, what we're gonna have is psi of x plus 2a. So it will gonna equal some c times psi of x plus a. And it will give us now c squared times psi of x. And now we can do the same thing the third time. So if we're gonna do it the third time, we'll have psi of x plus 3a is equal to, now it will be c cubed, psi of x, and you've got the idea, so we can shift it many times, and by the time we will reach psi of x plus n, a, we will accumulate the factor c to the power of n psi of x, right? All right. And we still don't know anything about this c prefactor, but now we can take this last equation and compare it with this our boundary condition. So, the head and the tail of Ouroboros should be at the same place, which means that this wave function of x plus an a should be equal to c to the power of a and psi x. But on the other hand, on the other head of the snake, it should be equal to psi of x, right? Which means that our c to the power of n is actually should be equal to 1. So now we will rewrite 1 as the complex number, so it's e to the power of I 2 pi n, where small n is some integer. So c has the form of e to the power of 2 pi n over n. All right. And in principle here, n can go through any integer, but physically we just demand that it goes through like 0, 1, 2, 3 to n minus 1, for example. Or you can start with 1 and it goes to n. It doesn't matter much. So, okay, I will need to erase something. Let me erase just this small thing. And I will continue writing here. So, what we've got is that this c is equal to e to the power I 2 pi n over n. And this c is actually this prefactor which we have had here. So this is to say that the solution of our one-dimensional Schrödinger equation with such periodic boundary conditions should have the following properties. So psi of x plus a should equal to e to the power of I 2 pi n psi of x. Right? So this just follows from just the simple trick that we demanded that our head and tail of the snake should be the same. So now this is just the condition for the wave function, and we actually can write down in a rather simple form the wave function which would satisfy this condition. So let me write it down. Psi of x. So if we write it down as e to the power of 2 pi n and a times x, some function u of x, and demands that u of x is periodic on the lattice, then this condition will gonna be satisfied. So let me now erase this also. So if we demand that u of x plus a is equal to u of x, so we will actually see that this condition will be satisfied. So how we can see it? So if we plug here instead of x, we will plug x plus a, then this function u of x will turn to u of x plus a, which is the same as u of x, and this exponent will give an additional factor which is exactly this. All right, so and now we can actually rewrite it. So this is already quite something that's quite similar to the Bloch theorem. That let's now, just for our further discussion, write it in the following form. So let's introduce this function u of x in the way that it has some exponent with minus I, k, and x, all right, and wave function psi of x. And right here we'll do a completely cheating trick. We will add this label kn for the reasons which will be clear in just a few when we will introduce actually the general statement of the Bloch theorem. But also you can see that this function u is labeled by this some number kn here, and actually the physical meaning of this kn is nothing else but the discretized wave number. So in 3D it will be wave vector. Okay, so this is just discretized wave vector. Okay, let me step aside so you can see the formulas. You can step aside like this. And let's just discuss what we have done. So the main trick was just putting this thing on the ring, and then with a number of manipulations we have shown that the solution to the one-dimensional Schrödinger equation on the periodic potential should satisfy the following thing. There should be some exponential function which comes just from the accumulation of the phase, and times some function u of x, which is periodic now on our Bravais lattice. And we will see that this will hold in the exact statement of the theorem as well. All right, let's now make the sketch number 2. So it's like Bloch theorem, sketch number 2. And in this sketch we're gonna derive something similar, but from a bit different intuition. So, and our main idea is that if we want to solve the Schrödinger equation, so let me write it down again. It can be one-dimensional, or it could be two-dimensional. Doesn't matter much. So, the perspective is following. So this is rather, again, it's more like a sketch. It's not a derivation. We will have the exact proof later. But the idea is following. So our Schrödinger equation is some kind of an abstract thing which describes some abstract particles, and then we need to come back to the experiment and we need to reconnect this equation to the experimental observables. And maybe it sounds a bit trivial, but we cannot measure any physical quantities which have the complex spectrum. So the spectrum of the physical observable should be real, which usually means that the physical operator should be Hermitian. For example, this Hamiltonian here. So this Hamiltonian here is Hermitian. So Hamiltonian is equal to the to itself Hermitially conjugated. But we are now facing a small dilemma because our Hamiltonian is Hermitian. Our energy should be thus be real. So energy is real. So energy of a single electron is actually quite a good observable. But the wave function is actually complex valued, right? So itself, the wave function is a bit not intuitive because it's not observable. However, we can now do the following thing. So if we multiply wave function by the same function but complex conjugated, that will give us psi x squared, and this function now will be real, which means that in principle it is observable, and it is observable. So it has a physical meaning of the probability density of finding an electron at the position x. So let me write just down, this is just probability density. So absolute value squared of the wave function has a nice physical interpretation, and it's now more importantly, so this thing is observable, while this thing and this thing, they're not observables. Right? So if we're now gonna look for something as psi x squared, it should be a good observable. And if we now come back to our Schrödinger equation in 1D, with our potential, okay, I have denoted as V of x before. So if V of x is periodic on some crystal lattice, which is to say that we have some arrangement of atoms, and because of this strict periodicity in the real space, we know from experiments, from our intuition, that the physical properties of the system shouldn't change if we shift it by the amount of A. So in other words, all the physical observables related to this equation shouldn't change after the translation of A if our Hamiltonian is periodic on this lattice. So this comes with the following condition, that the probability density squared at the position x and position x plus a, they actually should be equal. Strictly speaking, they are undistinguishable. All right. So, and now let's do a very similar trick as we did last time. So let's say that upon shifting by x plus a, our wave function can change on the complex number c, and now I will put the index a here. Which in particular means that if we will be looking for the probability squared, we will have something like probability of x plus a squared is equal to ca psi of x squared, but this also should be equal to psi of x. Psi of x squared. Psi of x modulus squared, which in particular it brings us to the following conditions for the CAs. So CA squared should be equal to 1. So in other words, again, what can change with this function psi of x is just some shift in the phase. So psi a can be now represented as so psi a is nothing by just some exponent to the power of some phase a. All right. So if we take the modulus squared, it will be always 1. And on the other perspective, if we shift it by several lattice vectors a, this phase will continue accumulating. So what we can do now is we can write down this C of A in the following form. So since this phase will accumulate with more and more A's we are taking here, so it should be something like I. I'm now dropping the prefactor here, but it should be proportional to A, and let's call this coefficient which is proportional as K. So in the way we defined here, it's not exactly clear what is the physical meaning of K, but it's something like the wave vector, so it's something like the wave number. And so at least it has it has the dimensionality of 1 over meter. So A has the dimensionality of meters or nanometers or angstroms if you want. So K times A should be dimensionless. So that's why this K should have dimensionality of 1 over m, 1 over meter or 1 over nanometer, 1 over angstrom, and so on and so on. So it has the same dimensionality as the wave vector, and it actually will be our wave vector. So, and now what we're gonna see is that when we shift our wave function psi on K on A, so what will happen is that psi of x plus A, it actually just accumulates this phase IKA psi of x. And actually in the very similar form we can write a similar expression for the 3D system, so it's quite easy to generalize now. So let me just put the vector on top of x, which means it's a two-dimensional or three-dimensional vector, and instead of r we will take all these translation vectors, and then we will have e to the power k a psi of x. So actually this is this is the Bloch theorem itself, but in this kind of sketchy way of introducing it, it's not yet clear what is this k. So we know that it should be something as wave vector or something as momentum, but it's not precisely clear. So, and the last thing, yeah, so this this index k should label a particular solution of the Schrödinger equation of the vector k. And so the last thing we can do here within this rather sketchy introduction. So what we can do is, again, we can introduce the function u. So in the similar way as we did it last time. So what I will gonna do, let me see. So let me just introduce the function u such that by definition it's minus a I k x. I'm writing again, everything is here is in 1D, and only this thing is in 3D. So this thing is again in 1D. So it's I to the minus ikx psi k of x. All right. And we can see again that this function has a very interesting property. That is, if you shift the argument x by a, so uk of x plus a, you'll have the following thing. So you will have here the exponent will give you minus ikx times minus ika, all right, and psi k. Due to this expression, it will give you the factor ika psi of x. So this exponent will cancel with this exponent, and you're left with just this exponent times psi. Let's keep this labels k, psi kx. So it's nothing but uk of x. So once again, we have a feeling that when we're introducing something on the periodic lattice, our solutions should satisfy either this condition or this condition, which is actually the same condition. What's important for us is that we are seeing that there is a factor which is fastly oscillating here, and then there is a function uk of x which is periodic on the lattice. All right. Okay, so what we have just done is we've just considered, constructed quite a simple observable, which is wave function module squared, and because in this system, this observable shouldn't change by shifting the whole system by a, we have come to conclusion that there is a specific condition for this wave function which would satisfy this one-dimensional or two-dimensional or three-dimensional Schrödinger equation in the periodic potential. So now, after we have introduced two rather simple sketches on the one-dimensional systems, with rather simple periodicity and rather simple, geometry of the unit cell, we are ready to state the general Bloch theorem, which is valid for any crystal, any Bravais lattice, any geometry. So, and this theorem reads like this. So, the eigenstates of this single electron Schrödinger equation, which have this kinetic part plus periodic potential V of x acting on the function psi x. So here V of x plus a is equal to V of x, which means that it's periodic and it holds for all the Bravais lattice translations A. So this eigenstate can be chosen to be just some plane waves times a function which is periodic on the Bravais lattice. So all this machinery which we have introduced before with Bravais lattices, Brillouin zones, it wasn't in vain, but it was in order to write down a rather simple formula. And this simple formula now reads this way. So this is our Bloch theorem. So psi is the eigenstate of the Schrödinger equation. It depends on x, and we have added here two indices k, which labels this plane wave, and one extra index n, which will be clear in one of the later lectures. But essentially, it means that this second-order differential equation can have multiple solutions, and this is an additional index which will label this solution. So this eigenstate is nothing else but the plane wave. So you have already met the plane wave in the course of quantum mechanics. So this is just the plane wave times this function u of x, which we have introduced on the previous slide, and this function should be always periodic on the Bravais lattice. So this is periodic on the lattice, right? So, and it looks rather simple. So if you remember something from today's lecture, please remember just this formula. So eigenstate is equal to plane wave times a function which is periodic on the lattice. And it essentially means the following thing. So if we have no term v of x, we are left just with some plane waves which just propagate in this space. And now we are adding some potential which is periodic on the Bravais lattice translations. And essentially what it means is that instead of this plane wave, we have now some plane wave which will be modulated in space. So let me just sketch it maybe in the way like this. So we have a plane wave which oscillates crazy fast, just this thing. Oscillates in space x. So this is this part which is given by this exponent. And then its amplitude is modulated by this function u of x, which is now periodic on the lattice itself. So this periodicity will be given by a. So this is the physical meaning of the Bloch theorem. And again, please remember just this one formula. We will now gonna prove it that it holds for all the kind of lattices. Prove exactly, but if you don't understand the exact proof, never mind. Maybe you don't need it if you go to the experiment, so you can skip those several minutes. But if there is one thing you want to remember by the next week, it's just this simple formula. One more time, the eigenstate is equal to plane wave times a function periodic on the lattice. So I will step aside. So, and this is the key theorem which we will be using. All right, we will now work on the proof of the Bloch theorem. And we will do it in the two parts. So in the first part, we're gonna write the same theorem, but in a bit a different form. So let me drop this index n for a moment. And what we will do is, let me also take a different color. So we will write this psi k as this plane wave ikx times the periodic part, right? And now let me put all the vectors. Okay. So this psi k is actually psi k of x. So let's see what happens if we will shift this function by the value of one of the translation vectors. So psi k of x, or let's say we will shift it by any translation vector, which is a capital. So if we're gonna do this, we will have now here the same factor ikx. We will have an additional factor ika, and we will have uk of x plus a, right? This function, however, the way we introduced it and the way the Bloch theorem says, this function is periodic on A. So this is nothing else but uk of x. So what we are left with is this prefactor ika times ekx uk of x, and this is nothing else but psi k of x. So we have eka psi k of x. So in other words, and there's like one line transformations, what we've got is that if we have the Bloch function, so the Bloch function is the function which satisfies the Bloch theorem, and the Bloch electron is electron on the lattice, so electron which satisfies Bloch's theorem. So if we have a Bloch function at x, we can write down the Bloch function at x plus a, which will acquire an additional phase factor ika times psi k x. So we have already seen this form in I think sketch number 2. So, and this is essentially, and this is the alternate form of Bloch theorem. Bloch's theorem. All right. So, if we want to prove the Bloch theorem in this form, we will see that it's actually much faster to prove this line, and then, you know, they're connected by quite a well, one-line transformation. All right, so let's continue. So in the part 2, for the proof of the Bloch theorem, we need to introduce a new concept, which is a translation operator. So let's define just some quite an abstract mathematical operator, which behaves in the following way. So let's denote it as T. So T stands for translation. So this will be the hat will mean that it's an operator, so we can distinguish it from simply numbers or simple functions. And let's say that's a translation on the vector A. So the translation operator will be defined in the following way. When it acts on some function of x, and it actually doesn't matter what is this function. It could be the wave function, for example, or something else. So when it acts on the function like this, the translation operator will shift this function by the amount of a. Right? So now if we are on the Bravais lattice, we can actually define the translation operator with respect to any translation on the Bravais lattice A. And then here instead you will have A. Okay? And in principle, your A on the Bravais lattice is n1 A1 plus n2 A2 if you're in 2D, and plus n3 A3 if you're in the 3D. All right. So this is our definition, and now we'll consider the Schrödinger equation. So let's write it just in a simple form. Hamiltonian operator acting on the wave function is giving us energy times the wave function, right? And now let's apply this translation operator to the both sides of this equation. So if we were gonna do this, what we will obtain is the following. So TA acting on H psi. On the one hand side, what will happen is that H will gonna shift by A because of this property, but also the wave function here gonna shift by A. Right? And on another hand side, you can rewrite the same thing as when it acts here. It will be just E. When you have translation acting on psi. Okay, let's write it down. Psi of x. So on this thing is nothing but E times psi of x plus A. And in principle, we can further massage this. That's the energy eigenvalue, and this is the wave function. So we can reuse this equation again and say that it's H acting on psi x plus A. And now the important thing which we need to use in this line is that we are working with the Hamiltonian, which is periodic on the lattice. So H of x plus A is nothing else than H of x. So this thing will be H of x as well. All right. So from here, we can see that so this thing kind of all right, let me write it here. So if you massage a bit this formula, it means that operator T times H acting on the, well, let me use the usual, TH acting on the wave function is the same as h ta acting on this wave function. So in other words, this ta is commuting with h. Right. Moreover, this translation operator has the following properties. So if we have ta and ta prime, so in other words, we first make the translation on a prime, and then the translation on ta, on a, acting on the wave function. So of course, so first we will shift it by a prime, and then we will shift it on a. But in principle, since it comes here as the linear combination of these translation vectors, that will gonna be the same as if we would act first with a prime on psi x plus a, or it's actually the same if we act with ta a prime on psi psi x. No, let me write it like this: ta plus a prime. So this is to say that like we have ta prime is equal to ta prime ta, and it's actually the same as ta plus a prime. So in other words, we are coming again to the conclusion that ta and Hamiltonians and ta and ta itself is a set of commuting operators. So, and we know this property of the quantum systems that if we have the set of commuting operators, it means that we can write in the same basis the eigenstates of ta will be the same as, so we can choose the basis in this way that the eigenstates of Hamiltonian will be the eigenstates of ta. All right. So maybe it looks a bit abstract, all these formulas which you see here, but the main goal is we have introduced some translation operator, and as we will see, we will not even need it explicit form. The main thing is that we can work in the same eigenstates as the Hamiltonian, so we can make certain conclusions about the eigenvalues of this operator ta within the same set of eigenstates of our Hamiltonian. So, all right, let's continue with the proof of the Bloch theorem. So, in the previous slide, we figured out that we can introduce this translation operator, which will have the same eigenstates as the Hamiltonian itself, which is to say that we can write down in the same basis that Hamiltonian acting on the wave function is equal some energy, which is the eigenvalue of this Hamiltonian, times psi, and in the same basis we can write down that the translation operator translation operator ta acting on the same wave function will give us some will return us some eigenvalue ca and times the same wave function. All right. So let's now use this. Let's now see what it means in terms of the properties of these eigenvalues. So let's again, as a small exercise, let's act with Ta prime on some eigenstate psi. So we will first act with A prime, so it will give us Ta C A prime psi, and now this is just a C value, so we can take it outside and act the second time with this operator. And essentially, since these are C values, we don't care about its order, but let me still write it in this way. So you will have this, and on the other hand side, we have the property that when Ta times Ta prime, so Ta times Ta prime acting on psi, that's nothing else but Ta plus A prime acting on psi, right? And this is nothing else but Ca plus A prime, so the eigenvalue now of this operator acting on psi, right? So, and now we have, by comparing these two equations, so they should be the same, so we come to conclusion that we have a funny property that Ca prime should be equal to Ca plus A prime, right? So, and well, it's quite a little cute equation, and it's actually very easy to satisfy this equation if this if our translation vectors A will sit somewhere in the exponent. In the other words, let's say that so one more time, we have a product here of some eigenvalues, but we don't know what are these C numbers. Well, we've seen from sketch 1 and sketch 2 that they should be exponents, and you know, if we will have something like exponent A times exponent A prime, then they will add this way, right? So let's see just some small examples. So for example, if we take instead of A, we'll take A1, which is just like one of our basis vector in the real space. So that would mean that CA1 should have some form e to the power of I. There should be this A. Or actually, let me write it in a bit different form. So let me write it in the form 2 pi xi, and we'll figure out the physical meaning of this xi just in a second. So in other words, like if we're dealing with the eigenvalues of these operators, there should be some algebra which is related to the exponents, and the fact that this C by the absolute value can be only 1, which we have seen in the sketch 1 and sketch 2, and that's connected with the fact that the wave function squared should not change upon the translation, so the eigenvalues of C should be modulus 1, so that's why we are writing it in exponent. So now let's consider a bit more generic case. So let's write this vector A as n(a1) plus n, so n1 and 2 a2 plus n3 a3 and if we do the translation on this vector and plug it somewhere in these equations, what it would mean is that the eigenvalue on this vector like this could be decomposed in the products of CA1 to the power of n1 times A2 to the power of n2, and this is CA3 to the power of n3. All right. So in the other words, if there is some thing, let's denote this psi1, we'll see the physical meaning just in a couple minutes. So if we introduce different psi1, psi2, psi3, so this will be nothing else but some exponent raised to the power I 2 pi n1 psi1 plus n2 psi2 plus n3 psi3. And again, here n1, n2, n3 are integers. Okay, so the statement is following. So all this one line, in particular this, can be rewritten in a much easier and simpler form. And in particular, it can be rewritten in the form as some vector k times a. And let's introduce some vector k, which will have the following form. So we'll introduce k, which has the form psi1 b1 plus psi2 b2 plus psi3 b3. And if we have had integers here, n1, n2, and 3, then psi1, psi2, psi3 are not necessary integers. Let me just write any numbers. Any numbers. So in other words, it can be like any vector. Any vector. Indeed, if we introduce k this way, then we can do the following thing. So let's just look what will be the product of k times a. So it will be, let me write it one more time. So it's psi1 b1 plus psi2 b2 plus psi3 b3. All right. And we are multiplying on this vector n, which is n1 a1 plus n2 a2 plus n3 a3. Right? And now this is nothing else but actually 2 pi times psi1 n1 plus psi2 n2 plus psi3 n3. So why is it like this? So last time we introduced the following notations. So a1 are this basis vector in the real space, and b1, b2, b3 are basis vector in the reciprocal space. And if you remember, so what we have introduced is this equation, ai times ab, scalar product, is 2 pi times delta ij. So delta is the Kronecker delta. It's equal to 1 if I is equal to j, and it's equal to 0 if I is not equal to j. So every time when we have b1 times a1, we will have 2 pi, which I put here. And every time when we'll have b1 times a2, for example, or a3, we will have zeros. And the same way here. Every time when we have 2, index 2, we will have 1. So this times this will give us 2 pi. And every time when we have index 2 times another index, we will have 0. So long story short, this reduces to this. So in other words, what we have just done is that, remember, we were writing this CA, so the eigenvalue of the generic translation operator on the Bravais lattice is equal to just I to the power IKA. Okay. Where vector k is certain wave vector, which was labeling our solutions. All right. So essentially that's it. Let me just erase something. So on the previous slide, we have shown that the eigenvalues of the translation operator CA can be written in the form e to the power of IK A, or if you have a generic vector A capital, you can put A capital here. And if you now remember how we introduced these eigenvalues, these were the following thing. So we have introduced the translation operator A, which is acting on the wave function at x, and it's giving us the value CA times this function psi of x. Right. And on the other hand side, if we would act with this translation on psi of x, it would give us psi of x plus A. So now what we can write down is psi of x plus A is equal to CA psi of x is equal to e to the power IK A psi of x. So in other words, we have derived the following thing: psi of x plus A, where A is any Bravais translation vector, will acquire a phase IKA psi x. So, and this is the Bloch theorem in its second form. So, see part 1 of the proof. In other words, we have proved the Bloch theorem through introducing the translation vectors. The eigenvalues of these translation vectors are certain C numbers which have modulus 1, so they just change the phase. And so the physical meaning of Bloch theorem in this form is that the wave function will acquire just a phase if you shift it by the Bravais lattice A, or in another form you can write it as psi of x is equal to the plane wave UK of x, where this is a periodic on lattice. Both forms of these theorems are good. Probably the deeper physical meaning has this first form which we have introduced, but we will use both of them for our further derivations in the next lectures. All right, so we have introduced the Bloch theorem in a couple of ways through the sketches. We have written the exact statement of the Bloch theorem, and then we have given the proof of the Bloch theorems through the translation operators. So if you don't, if you are a bit confused with the proof of the Bloch theorem, that's not a big deal. Just skip it. So what's the most important thing is just understand what it means. If you understand, that's good. But there are still a couple of remarks which we need to give here in order to proceed further. So let's just summarize a couple of general remarks. So the first remark will be following. So we have introduced this vector k, which has the dimensionality of the wave vector. So it is very tempting to assign hk and to say that this is the momentum of our electron as a quantum particle, because it behaves very similar to that. In particular, it has the correct dimensionality, and there's another way of seeing that there is a deeper similarity between hk and the momentum of the particles, which we're not doing here. But for example, if you include the external magnetic fields, it will couple through the minimal substitution to this hk. So in the similar way as for the classical particles, you will have coupling between, you will introduce the vector potential, which will shift your momentum. So there is a very big temptation to say that this is our momentum of our electrons. However, strictly speaking, this is not the momentum. And in order to see this, let's actually write down the momentum operator explicitly. So the momentum operator, the way you introduce it in quantum mechanics, is minus I h bar times the derivative, essentially. Yeah. So this is d over dx. So, and if we will act now with this operator psi on some function psi, operator pi acting on some function, wave function psi, which satisfies the Bloch theorem. So, which is to say, we have certain electrons on the lattice, and we ask, is this thing their true momentum? So here's what we are doing. We're acting with this operator pi on a certain Bloch wave function. So, and what it will give us is the following thing. So this is I h bar nabla, just the operator of momentum, and here we will plug in explicitly the Bloch solution in the form of the Bloch theorem, which we have written just before. So one more time. The eigenstate, according to the Bloch theorem, is nothing else but the plane wave times some periodic function. And now you know we need just to act with this operator on the product of these two. So when we will act with this on the exponent, it will give us minus I times I. So the minus sign will cancel, and we will have just some h bar k times eikx ukx, right? But this is nothing else than, again, this Bloch state. So we are kind of happy, but that's not all the story, because we now need to add the second term, which is this derivative acting on the second term. So we will have an extra term which will be I h let me see. Let's write it in the following way: IAKX, and then we have nabla acting on UK of X. So and then, you know, if there was no term like this, so if there was no term like this, we would be quite happy. Now we will not be happy, but in this case hk would be equal to momentum. So why it would be like this? So look, we were acting with the momentum operator on some eigenstate, and it was returning us hk times the same eigenstate. So if there was no term like this, we could say that hk is the eigenvalue of pi. However, we now have the second term, which generically is not proportional to this function psi, and generically it will modify our momentum. So momentum will be actually defined up to the translation on the reciprocal lattice. So long story short, hk has a physical meaning very similar to momentum, but it's actually not the momentum. So and it's actually what we call the quasi-momentum. Or in some books you'll also find the crystal momentum. So what's important to understand is that why this is happening. And in order to do this, we need to recall a very nice theorem by Emmy Noether. So Emmy Noether, I think in 1918. So Emmy Noether. So she was a German mathematician who has introduced a number of very important concepts and theorems. And one of the most important for the physicist is the theorem which is saying that every symmetry in the equations of motions, for example in the Schrödinger equation, is related to the certain conservation law. So for example, symmetry with respect to the reversal of time, so if you send t to minus t, means that your energy in the system is conserved. And in the very similar way, the translational symmetry the full translational symmetry, where you can shift x by a very tiny amount dx. It means that your space is uniform, so it means that you can introduce momentum as a good quantity, and it's conserved. Momentum is conserved. Now, when you have a crystal, well, let me write again in 1D, for example. But you're actually breaking this continuous translational symmetry, because if you shift just by dx, your physical properties will change. So, of course, if you shift by a, which is a discrete symmetry here, we will talk more about the symmetries in the very end of the course. But just to say that once we introduce the crystal lattice, we are breaking this translational symmetry, and that's why momentum is, strictly speaking, not a good quantum number, and that's why we actually cannot define momentum, because it's actually not conserved. In particular, you can add to the k. Well, if you want, we can write h bar here, but let me drop h bars here. Okay, let me write with h bar. So we can add to any k an arbitrary reciprocal vector j. So you remember our j was defined on m1 b1 plus m2 m2 b2 plus m3 b3. So actually, if you do this machinery carefully, you will see that instead of conservation of momentum, you have a very weird rule, because this momenta essentially always appear in the well, not always, but the way it's introduced in the Bloch theorem, it appears in the exponent. And this exponent, if you shift by the factor by the phase of 2 pi, which would be guaranteed by this, so nothing will change. So long story short, because of this, you don't have the conservation of momentum, but you have the conservation of momentum up to the any number of these reciprocal vectors b1, b2, b3. And this is the peculiarity of this Schrödinger equation on the lattice, and this is why, because we are breaking the translational symmetry, we don't have momentum as the conserved quantity, and that's why, strictly speaking, this hk will not be our momentum. And in principle, if this will also give us lots of simplification. For example, if our hk will be too far, we can always add any number of this j to return it to the first Brillouin zone. So if we will have certain physical properties as a function of k, you remember our first Brillouin zone is defined from minus pi over a to plus pi over a. So it's here. So if our momentum is somewhere far, we can add this j. We can add this j, and our quasi-momentum will return to the first Brillouin zone, which is a good feature. All right. A couple of concluding generic remarks. We have introduced this Bloch theorem, and in particular, what will be important for us is that these Bloch states can be shifted by the amount of the reciprocal translation vector, and nothing will change. So what we can write is this psi n k of x. So n is some other index, the meaning of which we will understand only on the next lecture, but it will refer to the electronic bands, and it's connected to the fact that the Schrödinger equation can have more than one solution. So, and essentially, if we rewrite it in the following way, if we shift k by any reciprocal translation vector j, this wave function still stands. And more importantly is that because the wave function have this periodicity in the reciprocal space, so we are talking now about reciprocal space, then the energy, which are the eigenvalues of the Hamiltonian, so the energy will have exactly the same property. So we can shift energy by any amount of j, and the energy will remain the same. Importantly, this in particular means that energy is a discontinuous function at the boundary of the Brillouin zone. Maybe this sounds a bit abstract for you, so let me give you a simple example. So let's consider a 1D Schrödinger equation. And let's write it in the following form. So let's write it in the form as always, we have minus h squared over 2m d2 psi over dx squared plus, let's put a certain alpha here, v of x, psi of x, and then this all gives us energy times psi of x. And now let's assume that v of x has this good periodicity on the lattice, which then so our psi satisfies the Bloch theorem. So electrons kind of fill our underlying lattice. And now let's consider the following thing. So we have these electrons. They are in 1D. So these are atoms. So these atoms are creating certain potential V of x. And then in principle this potential can be quite strong or it can be quite shallow. So, and the reason why I introduce this alpha here is, let's assume this alpha controls the strength of this potential. So how broad and how, you know, how deep is it? So, and let's, for example, change alpha from 0 to 1. So if 1 is strong, like electrons feel all this potential, and that's fine. But now let's switch off alpha continuously, and let's tend alpha to 0. And in this limit, you know, this term it will essentially cancel, but electrons will still feel some kind of periodicity. So there will be a very shallow potential here, and electrons which will be moving on top of it will somehow still feel this potential, but they will be more and more reminding these free particles. So in principle, they should remind this free particle dispersion, h squared k squared over 2m. But now they're still feeling this, the remainder of this very weak potential. So, and what happens if we now will sketch this thing in the reciprocal space? So with our knowledge of the Brillouin zone. So E of k. Okay. So let's say this is our first Brillouin zone. So in this course we will be talking mainly about this. So this is first Brillouin zone. So this is 0. By the way, point 0 in the Brillouin zone usually have a special name. It's called gamma. So it's called gamma point for some reasons. You will see this in the exercise. Anyway, so this is 0, and then in principle you have, you have here 2 pi over a, you have 3 pi over a, and here you have minus 2 pi over a and minus 3 pi over a, right? And let's first focus within this first Brillouin zone. So let me push these dashed lines like this. So this thing is our first Brillouin zone, the way we defined in the previous lecture. And you know, if our electrons were if our electrons were just free particles, so what would happen is that we have this quadratic dispersion. So it goes as a quadratic function somewhere here, but that's it, right? So up to the moment, that's it. So, and in particular, in this particular simple case, it means that this equation E and K is equal to N and K plus G means that if we shift energy, if we shift this quasi-momentum by the value of G, which is, in this case, G is any integer times 2 pi over a times integers. So our energy should remain intact. So before doing this, so let's continue with our parabola. So let's draw this parabola. Now it hits here. So this is the boundary of our first Brillouin zone. Let's draw it this way. And now I will take a different color. And now I will continue drawing this parabola, but it will go up with a different color. Maybe. Well, that's kind of a parabola. Let's imagine that's a parabola. All right. And there is a reason why I'm drawing it with a different color. Okay. So, and now, because this relation holds, it means that in particular, if we shift everything by nk, by 2 pi over a, which is, I'm running out of colors. So if we shift, there's a green color, but it looks almost like the yellow color. So if we shift this by 2 pi over a, so we can shift the entire parabola here and entire parabola here. So let's do it. So yeah, let me do it in the sketchy way. Like this. Well, and then in the same manner we can shift this parabola in the other side. So like this, and again it will go up here, it will go up here, and in principle we can shift it further, so there will be other parabolas, you know, here, and another parabola somewhere, well, somewhere here. So this is precisely the statement of this formula. Now, importantly, this formula also tells us that they are always intersecting at the same point in terms of energy. So the energy at the boundary of this Brillouin zone is the same. So this point stands at the same height as this point and this point. And actually, we now can connect it with a different color. Let me connect this all with the blue color. And we have a second thing which, again, there will be some intersecting here, again in the same points, but we now can connect it with a different color, which is supposed to be yellow color. I don't know, can you see yellow or not? But we'll have another thing like this. So, long story short, instead of simple parabolic dispersion, we arrive into some quite intricate situation. And as we will see in the next lecture, actually, if we allow finite alpha here, it will open, so as we say, the gap. So there will be a space where these functions are not touching. And now it looks like all these electrons, they exist in this like one function. So this is called the band. Like people are gathering in bands, and electrons are also gathering in bands. So kind of a similar thing. So it's a band, and this will be another band. We will see later what it means. But long story short, instead of quadratic dispersion, just because we have added the potential, we now have this crystallographic notion of how the electron's energy depends on this quasi-momentum. So remember, K is not a momentum, but it's a quasi-momentum. And then it repeats endlessly in space like this. So it's periodic on this J, which is 2 pi over A integers. Right. So in the exercise in class, you will have a similar problem with the also free electron gas, which means you neglect this term for a while. So, but in 2 dimensions. So you will play a bit you'll get familiar with this concept, but in 2 dimensions. Now, for the purposes of most of discussions, we actually don't need this extended quasi-momentum space, but we actually can restrict ourselves only to the first Bruggen zone, and then electronic dispersion will look just like this. So I will erase everything which is outside of the first Bruggen zone, which is defined from minus pi over a to pi over a. Alright, so this is k. Okay. And again, here k is quasi-momenta, but so for the free electrons they touch. So, but for multiple, like if you open multiple scientific papers, you will see that people are already tired calling it quasi-momenta every time, so they will call it simply momentum. So that will not be a mistake if you do the same within this course or the exam, but just remember that this is the quasi-momentum for the reason which we described before. But in the similar way as the momentum, there is, relation between energy and this wave vector k. So hk will be our quasi-momentum, and it shows that the electron will disperse on this lattice, and we can again define so since there is some finite dependence of ek of energy on this k, so we can define the velocity in the similar way as we did in the as we have done in the Sommerfeld model. So it's dE over dHk, right? So, and now we're coming to a very interesting situation when there is always certain velocity here, because so electrons are always moving, and this velocity will be generically non-trivial, in the sense that if you remember when we started the course with the Drude model, we thought that all electrons are solid balls. They are, flying in this like space. They are colliding with ions, atoms. So, and then they are scattering, and that's why their velocity decreases. But actually, if we treat the problem in the correct way, in the quantum mechanical way, so our atoms now represent certain potentials, and yes, and the dispersion of electrons got modified in the way we see here, but actually there will be still the velocity, and it will not be decreased. So electrons will travel essentially forever in these materials, and this is kind of like a very striking difference with the Drude model, and it's very important to overcome this difference. So for the exercise session, one more time, you will have the free electron gas, but in 2 dimensions. You will play with the 2-dimensional Bruggen zone, and will sketch a similar thing, but along a certain high symmetry path in the 2-dimensional Bruggen zone. And what we will do next time is that we will see how including the weak coupling to the atomic lattice will change our dispersion. And then in the lecture after, we will consider the strong coupling. So the weak coupling is called the nearly free electron model, and the strong coupling is called the tight binding. And they will give, of course, they will give different solutions, but these solutions will be still qualitatively similar. So, and we will come to conclusion that the truth is somewhere in between of nearly free electron gas and the tight binding model, because they will give us a very similar, a qualitatively very similar description. So, and just to conclude, if you remember something from this lecture, please remember that our Bloch theorem can be written in the form as a plane wave times some function which is periodic on the lattice. So if you remember just this, you will be quite good for the next few lectures, and in general you will sleep better. So see you next time.